I'm on a roll. I'm going to keep going here. All right, so we told you before, or I told you before, that a lot of times this is going to be given to us. So kind of the standard way, or a way that they give us the data, we won't necessarily see screenshots like we do here in our calculator when we're doing the line of best fit. A very common way that we do it is a statistical package called Minitab. So in Minitab, we want to make sure that we can see all of our points here. Notice that we have our miles driven, so that is related to our X. And again, we're back to our truck and our slope, right? Our truck, the miles driven and price. So here we have the miles driven, so there's our slope. There's where our y-intercept is. And then S, we know that's a standard deviation of visuals, so S is nice. S is S, even though we have a capital here. And then R squared is going to be right here as a percentage. So we want to make sure that we can grab that data out of a Minitab. That's very common to how they would give us the data in a graph, in kind of a data display here, which is Minitab. And a lot of times you're just going to tell us that R squared equals this, S equals that. Here's the slope, here's the constant. Remember that we did this in we're doing this in chapter 3. We're doing this till the tail end of it. But actually, this is something that if you are working from chapters 1 to 12 or 13, someone did really early in the semester, right? So this is something that was definitely covered by all groups. So just because we are doing this here at the end, doesn't mean like, oh, they probably won't have it. We're really want to know and talk about what this is because it's important here. We think that it's going to pop up. Okay. So here's an example, just a quick one, that's from the 2012 AP Stats multiple choice. And this is in your packet on page 10. So the question read this year, the computer output below shows the result of a linear regression and analysis for predicting the concentration of zinc in parts per million from the concentration of lead in parts per million found in fish from a certain river. So notice what we have here is we have the Minitab output. And it's really important as for know. Here, S is really easy to find. R squared is easy to find. We have the slope here, and we have our constant here, which is 16.3, okay? So let's take a quick pause and just try to figure out what is the correct choice here. Which of the following statements is correct interpretation of the value of 19? All right, let's sneak back. What was 19? All right, 19. Okay, that looks like it's going to be our slope. So remember that slope is change in y over change in x, predicting zinc per x. So we're looking at our zinc is going to be our y because that's what is predicted, right? So we take a look and average, there is a predicted increase of 19 parts per million for every zinc for every 1 concentration of lead. All right, so that's what we're looking for here. We're looking for B to be an answer. A is not our answer because it switched the X and Y. C and D are both trying to pretend that 19 was our y-intercept. And notice E, they're sneaking in and trying to get here. This is how we talk about what S is, but we know that S isn't 19. We can say that S is the 16.17 here. Okay. So if we were doing this by hand, which we don't have to worry about, these are equations that we would use. This is very not often used in a normal year, and we don't think that we would have it. But this is what would be nice. This is how we would find what the slope and the y-intercept would be. So slope is very easily just taking our r and multiply the quotient of the standard deviation of y or the standard deviation of x. And the y-intercept is by taking what we have for our mean of y minus b times the mean of x. So we can see that we could create this line of best fit ourselves just by taking x and y and finding the means and the standard deviations. So it's not something that we're going to focus on, but it's something to know. One thing, little thing that's really nice to know here, and sometimes it pops up, but more in the multiple choice you have to worry about, is the line of best fit always goes through the point mean of x, mean of y. It always cuts to the middle, kind of like a teetering point there. So this is what your formula page looks like. We can see that it will remind us that y predicted is a plus bx. And if we needed to find those b's and the y's, they're there. Again, very uncommon that we have to do that in a normal year versus this year, but it is on our data, it is on our equation sheet. Another thing we want to be careful of is talking about outliers and what's called influential observations in regression. So an observation is called influential for statistical calculation if removing it would markedly change the result of our calculation. Points that are outliers in the x direction of a scatter plot are often more influential for the least squared regression line. So if you were asking me to mark a point on the scatter plot that would have a large residual but not be very influential, a large residual would mean that it's really far away, but non-influential means that it's not far away in the x direction. So here I'd have a point here in the y direction. This has a very large residual, but it's not a far away from the data in the x direction, it's in the y direction. So this is going to be a large residual, but it's not very influential. What if you were asking me to mark a point on a scatter plot that would cause the slope to increase significantly? So where I might mark this point is up here. Notice that this is far away from the x. This data is probably centered about right here. So when I put an x away from that center and far away, the line of best fit is going to chase that line. And I'm going to show you a dynamic model in just a second. But if I did this here, this line is going to chase that line. It's going to change and it's going to make the slope go up. What if you asked me on a scatter plot to make a slope that would decrease significantly? Well, then I'm going to put the point down here because this line was going up, it's positive. But if I put that point down there and this line is going to chase that, it's going to teeter-totter. Let me show you something real quick. Let me pop out and show you this in Fathom. So here I have this again. I have my carbs versus fat, and I'm going to put my regression line in. Where'd it go? There it is. Okay. So if I take this point right here, notice that when I take this point, I'm going to make this a little bit bigger. We can see down here, here's my R squared. So only about 55% of the variation in fat can be explained by the linear relationship it has with carbs. I'm going to take this point and I'm going to move it. Notice that when I move it, the line changes a little bit, but my R squared doesn't change that much. And that's because I'm kind of sitting here in the middle of the data, right? So I can still have a big residuals. Now it is changing the line a little bit, but not too much. Now, look at the big difference here when I'm moving X. Notice how the line chases it. I'm moving it down, so the line is moving down, right? If I pop it and go above, it's chasing that. This is super influential point. This one point being far from the data is just making that line change. It's making it chase all over the place. Again, points within the data, not too much. Not too much here. Now, allow me, if I may, to move out a little bit here. So I'm kind of zooming out a little bit, right? Notice again that a point that's close to the data here isn't changing too much. But this point here, let me move it now even further away in the x direction. All of those points on the left show a positive relationship. But this one point, because it's so far extreme out here, right? That one point is so influential. Look how it's dragging the line towards it. No matter where I go, that line wants to chase it. That's just terrible. This is an influential point. If I were to move this influential point, let's say I were to remove this point here, I'm just going to delete it. Well, I just deleted the whole graph. That's not what I wanted to do at all. Let's try that again. Let's say I just take this point here. I'm going to get rid of that point. I'm going to cut that case. Notice how that popped, okay? By putting that point in and then removing it, that drastically changed what we have. That point is influential, okay? I'm going to put that point back. I'm going to put that point kind of back where it was before, kind of over in here. Now, what would happen if I were to delete this one right here, 8? Let's delete that case. Wow, that didn't really move at all, did it? See that again. Here's this point. I'm going to make it go away. Because removing that point didn't really change that, that point is not seen as influential. So again, an influential point, right, is a point that would markedly change the result of the calculation if I were to remove it. So let's talk about things that we've learned about regression and correlation, some things we have to be careful of, and some things we have to watch out for. Number 1, remember that correlation is the distinction between an explanatory and response variable. That's important in regression, okay? We need to know which one's explanatory and which one's response, because X is trying to explain what Y is doing. X is trying to explain the response that Y shows. Okay. Here, miles driven in price in dollars, if I'm saying that the change in miles driven expands the price, take a look at what happens if I change that. If I do price in dollars per miles driven, okay, that's a little bit different. But would it make sense to say that I'm going to use the price to predict the miles that are driven there? Okay, maybe it does. Maybe I can say that a higher price, which we see here, right, means that there's less miles driven. So we definitely want to make sure that we take a look. By switching the X's and Y's, notice that the R squared didn't change. The model is still as effective or not as effective as we saw, but we really have to be careful because both our slopes and our intercepts changed. So it's really important that we're distinguishing and talking about the explanatory and response variable. Another thing that's important is that correlation and regression lines describe only linear relationships. This is one of those things where you really have to be careful and you have to catch this by yourself. Remember that when we're doing hypothesis tests and confidence intervals, the calculator doesn't know to check the conditions for us. It just does it. We have to check it for ourselves. Notice that in this first example, maybe it's appropriate here to use the model, but this definitely isn't looking at the curve. This one, a model here, we would be worried about that one outlier. And this one here, we have a whole grouping and then we have a point out. But guess what would happen if we were to actually run the model on every one of these? Every one of these would have the same correlation coefficient, where only it was probably perhaps appropriate to use a linear model here, that linear correlation coefficient. So we have to be careful. We have to know when it's appropriate to move forward, because if we ask the calculator just to do it, it can't catch that for us. Another thing that we have to be careful of is that correlation and least square regression lines are not resistant to outliers. We saw that when we were looking at influential points, that your line is going to chase those outliers. And the further away that they are in the X direction, one point can really mess that up. So we have to be careful. Our regression lines are not resistant to that. So we have to be careful when we see those outliers and trying to guess what the model is there. Okay, we can see kind of a bounce around here of just by popping in and out this 19th child. So basically we have this set of data, right? And we pop these points in, and just by popping in points that are here far away from the X or here far away in the Y, that we can change those models. And again, notice that this child 19 was popped in. It didn't really change too much because it was a movement in Y, but child 18 here has popped out. It really has a line chasing that from what we have here. Another thing that we really need to be careful of is association or correlation does not imply causation. Remember that there's no causation without experimentation. Another big thing we have to be careful of that they're always going to try and get you on is correlation does not mean causation. When we study the relationships between two variables, we often hope to show that changes in the explanatory variable causes changes in the response variable, and a strong association between the two is not enough to draw those cause and effect. If we want cause and effect, we're going to have to do that experiment. So sometimes an observed association really doesn't affect that cause and effect. An association between explanatory value X and response variable Y, even if it's very strong, is not itself good evidence that changes X and actually changes it. Remember, we've talked about probably in class how we would have, when we have a fire, right? We would say that when there's more firemen or when they show up, there's more property damage. And maybe we were looking at that data and we're saying, wow, the more fire that we had, the more firemen that show up, the more property damage. Does that mean that even if there is a strong correlation, that more firemen showing up is causing there to be more property damage? There's probably a confounding variable there. And the confounding variable there is probably the strength of the fire. The strength of fire, if it's a stronger fire, it's going to have not only more firemen showing up to try and fight it, but it's going to have more property damage. So we have to be careful just because we see that association, it can't be that causation. I love this comic. I used to think correlation implied causation. Then I took a statistics class, now I don't. Sounds like that class helped. Well, maybe. Classic. Please remember, correlation does not mean causation. In this section, we did a lot of things. We talked about how to interpret the slope and y-intercept of a least squared regression line. We use the least squared regression line to predict y for the given x. We calculate and interpret the residuals and their standard deviation. We explain the concept of least squares. We determine the equation of the least squared regression line using a variety of methods, constructed and interpreted residual plots to assess whether a linear model is appropriate, assessed how well the least squared regression line models the relationship between two variables, and described how slope, y-intercept, standard deviation of the residuals, which we call S, and R squared are influenced by outliers. So what is it time to do? It's time to do homework number 6 and then move on to the chapter review. Remember in homework number 6, what we're focusing on is identifying the equation of the least squared regression line from computer output. We want to make sure we talk about why association doesn't mean causation, and then recognize how the slope, the y-intercept, the standard deviation of the residuals, which we call S, and R squared, the coefficient of determination, are influenced by extreme outliers. Okay. So again, just take a look. See what we have here. Go back to those dynamic models if you want to take a look. Reach out to us if you need some more help. And we should be looking at homework number 6 and the chapter review. Thanks for joining us. I hope that that helped out a little bit. And I hope that if you have any questions that you're reaching out and getting some help. Okay. So I'm going to stop the recording here, and I look forward to your questions.